Good evening, everyone. Thank you for coming to tonight's Tech Talk. We are here joined today with Dylan, who will be taking us on a deep dive on message brokers. I will be moderating this talk this evening. If you have any questions, please feel free to reach out to me through direct message, and I will present those questions at the end. We will answer as many questions as time allows. Before we get started, please let's unmute ourselves and give our speaker a round of applause. Amazing. All right, Dylan, take it away.
All right, thank you, Brian. Good evening, everyone. Well, right before I begin, I'd just like to thank Jeannie and Bracklet for sponsoring this talk, and let's get into it. So just a quick overview of what I'm going to be going over today. First, what are message brokers and why do we need them? And then a couple of the main message broker models. And then I'm going to go into two of the most popular message brokers and get a little deeper into them. So first of all, so what is a message broker? Well, from a high level point of view, a message broker is a piece of software that manages communication between different services, different applications, different devices even. By minimizing the need for mutual awareness between applications, message brokers can implement decoupling. And the most important function of a message broker is to take a message in from one application or service or device or whatever it may be, and a message in this case can be just about any piece of data, process that message or data in some way and send it on to another application or service. The app that sends the message is known as the producer, and the app that receives the message is known as a consumer. So why do we need message brokers? So what makes message brokers so important in an increasingly decentralized and distributed software world? Well, the biggest advantage really of message brokers is that they affect decoupling, like I mentioned. So sending and receiving messages between applications or services has always been necessary in software development. But what happens when the receiving application isn't running, or there's a firewall or another network in between them, or they might not be written in the same language, or maybe the network is just very slow? Basically, there are a ton of problems that can prevent effective communication. And message brokers, by removing the need for direct communication between applications, they can prevent these issues from arising in the first place. Another important benefit that comes from this decoupling is that by reducing the interdependence of different services on one another, it makes scaling services much easier. And since the message broker can exist on its own machine, it can take some of the computing load off of your service and improve performance. So how do they actually work? Well, to get into that, I'm going to talk about the three main models of message broker: point-to-point, publish, subscribe, and distributed log. And the simplest form of message broker is point-to-point. In this model, when a message is sent to the broker by a producer, it gets added to a first in, first out queue so that messages are consumed in the same order that the broker receives them. And in this design, there's a one-to-one relationship between producer and consumer so that each message is sent and consumed only once, which makes this a useful model for things like financial transactions, where you need a guarantee that each message is only processed once. The next model is called publisher subscriber, or pub sub, and it operates similarly, but with some added layers of complexity to make it a little more flexible. So in pub sub brokers, messages still get added to a queue, but there can be any number of queues, and each queue has an attached name, which usually describes the type of messages they contain. And these names are known as topics, and generally they relate to some part of the business logic. And any consumer that wants messages from a topic simply has to subscribe to it. So there can be, in this model, a one-to-many relationship between producer and consumer. And also because the producer only needs to know the name of the topic to send a message to, and the consumer only needs to know the name of the topic to subscribe to, pub sub brokers help to decouple services even further and help scale out applications as well. The third model is called distributed log. And the main difference between this and the other two models is that as messages are sent to the broker, instead of going into a traditional queue, they're stored in what's called a log. And rather than being deleted once they're consumed, they're stored in the log and they can persist there for really any amount of time, which is just up to the developer to configure. And inside the log, messages are still stored in order that they're received, but each is assigned what's called an offset, which is basically a key that allows them to be identified. And when a consumer connects to the broker, it asks to start receiving messages from a specific place in a topic, and it can be made even more specific because the topics are themselves divided into what's called partitions, which effectively act like sub-queues. So a consumer can subscribe to a certain partition of a certain topic at a certain offset. And because the messages are stored and accessed in a central location, as well as the reliable nature of this type of broker, because of replication, mostly, it is often used in event streaming applications, which is to say, applications that need to process data in real time. So next I'm going to talk about two of the most popular message brokers, just to get a little deeper into how they work. So the first one is RabbitMQ. It was released back in 2007 and is one of the most popular publisher subscriber message brokers. So RabbitMQ itself comprises this exchange, which essentially acts like a post office. It takes in messages and it routes them appropriately, and a number of queues, which are attached to the exchange by something called a binding, and that's referenced by binding key. And RabbitMQ has a few different types of exchanges, which help make it pretty flexible. The first type is called fan out, in which messages are sent to at just every queue that the exchange knows about. The second one is direct, in which a message, when it's sent into the exchange, it gets a routing key, which gets compared to the binding key. And if they're an exact match, it will get sent on to the queue. The next one is called topic, which works similarly to direct, except between the routing key and the binding key, there doesn't have to be an exact match. It can be a partial match. And the fourth type is called a header exchange. And in this exchange, the routing key is ignored completely and messages are routed according to their header. And finally, the RabbitMQ's default exchange, the routing key isn't tied to the binding at all, but it's tied to the name of the queue itself. And so in RabbitMQ, because the routing is based primarily on message metadata, the developer can choose what type of exchange, and it allows for a great deal of flexibility, and is part of what makes RabbitMQ so appealing. Now I'll quickly going to dive into Apache Kafka, which was released in 2011, and it's a very popular event-driven message broker, and this is one that utilizes a distributed log. So, and Kafka itself is a distributed service. It runs as a cluster, which means it can span multiple servers and even multiple data centers. And it partitions and replicates records in such a way that many users can use an app without sacrificing performance. So Kafka is an event streaming platform, meaning that events are streamed out of producer apps, and other apps that want to consume them can subscribe to that stream. And events in one service can trigger events in others. So it can be used for things like messaging, location tracking, or data gathering, and things like that. Apache Kafka itself is built on 4 core APIs, and I just want to talk about them a little bit. The first one is the producer API, which, like the name suggests, allows apps to produce streams of data, which are streamed to topics, and they can persist in storage, like I mentioned before. The second is the consumer API, which subscribes to one or more topics, and it can consume data in real time, or since the data is persisted, it can consume older data. It's just up to the developer. The third one is probably the most powerful feature of Kafka, is the streams API. And it essentially leverages both the producer and consumer APIs to create streams and in which data can be analyzed, aggregated, and transformed in real time. And then finally, the connector API is basically for allowing one integration to Kafka to be written for one service and then reused. So, for example, like if you have multiple MongoDB instances and you want to connect them all to Kafka, you don't have to write the same boilerplate code over and over. You can just use the connector API. So that was just a pretty quick overview of both, but the question is, of course, which one should I use in my application? And like any engineering decision, it depends on your use case. If you're going to be streaming large amounts of data, and especially if you want to do something with that data in between services, then Kafka is probably your best choice. Whereas if what you need is flexibility in the implementation of your message broker, or communication between apps or services written in different languages, or you need messages to be delivered in order, then RabbitMQ might be a better choice. Kafka, because it persists data in its store, it means that you can access data more than once, and you can replay events if you want. But because of that extra storage, it also means more overhead. RabbitMQ, on the other hand, while it's more flexible, it's language agnostic. It also has no native streaming support, and it requires more brokers overall if you have a large distributed system. So it's up to the developer to choose what's best for their use case. Of course, these aren't the only options available. There are plenty of other message brokers available out there. Azure Service Bus, Google PubSub, Amazon SQS, Amazon Kinesis. There are lots of others. So the important thing to take away here is that message brokers provide decoupling of services and applications and devices, which is becoming more important as like the Internet of Things becomes a larger paradigm. And it makes communication between these things more efficient, more effective, and more secure. Here are some of my works cited. And if you want to get in touch with me and talk more about message brokers or anything else, you can. Thank you.
Awesome. All right, everyone, let's unmute to give another round of applause for Dylan. All right, really nice. So let's address questions from our audience. Our question comes from Timmy, and it says, so what happens when a message is actually causing the receiving application to fail? Will it just keep getting delivered and causing errors?
Yeah, that's a good question, actually. And it's a pretty important thing for a developer to consider. So usually, so if there's something wrong with a message that's causing a problem, and when it's getting received by the consumer, it's called in message brokers a poison message. And a lot of the handling of poison messages is really up to the developer. It makes like error handling very important. You really just have to make sure that the messages and the data you're sending aren't corrupt and they're not going to cause errors. But there is a way for message brokers to deal with it in a way. When there's a message that gets delivered repeatedly without success, they can take it out of the queue or out of the subscription, and they put it into something called a dead letter queue. But that's also still up to whoever's implementing the message broker to make sure that there's a way, like something to trigger that, to send those messages into the dead letter queue.
Awesome. All right. So that's all the time we have. So we will conclude our talk. Thank you all for joining us and have a great night.